Welcome back, and we are going to continue on reviewing some concepts that we've covered before. So in this lesson, we're going to be covering the periodic table. So you've covered this before in grade 9 and grade 10. We're going to take a little bit more look at it in a little bit more detail in this lesson. So essentially, the periodic table has a bunch of trends in it that you might not be aware of. So every year in chemistry, I try to show you a few new trends that are present in the periodic table. The periodic table is actually one of the best tools that you can have as a chemist. The more you know about the table, the less you actually have to memorize, and the more you understand about chemistry. So I want to give you a bit of a background first about the periodic table and how it was actually developed. So before we get to the modern father of the periodic table, I want to touch on this gentleman, John Newlands, a little bit. So John Newlands actually was the first one that really started sorting elements. So how he actually sorted elements, put my face back up here again, how he actually sorted elements is by atomic mass. So he actually went through and he ranked elements by atomic mass. Now, if you take a look at your periodic table, you'll see that elements do increase in order of atomic mass. So this actually wasn't a bad way to actually rank. However, it didn't show all the trends. What Newland did notice is that elements with similar properties occurred every eighth element. That's true after helium. So every eighth element, he was noticing that elements with similar properties were happening about every eighth element. So he called this pattern the law of octaves. Then came around the gentleman that you probably heard of before, Dmitry Mendeleev. So if I've had you before, I've showed you a video about Mendeleev. You know that I think Mendeleev's a genius. So I do have that video linked below. It's a crash course video. Take some time and go ahead and watch a little bit about how brilliant Mendeleev was in the way that he organized these elements. So he's the known father of the modern periodic table, and he actually assembled the periodic table by mass, but he looked at a few more patterns. So he started going through by mass, but then he actually placed elements that had similar properties in columns. So instead of just listing by mass, think about this. If you were listing elements by mass, you would have an endless list from 1 all the way to 118. What Mendeleev did is he started noticing that not only am I going to increase by mass, but I'm also going to use the columns going down to help to rank similarities. So anything that had a similar properties went in the same column. So for example, the first column all had similar properties. The second column all had similar properties. So he picked up on that octaves law that we talked about before Newlands, but he actually would every eighth element go back to the beginning, every eighth element go back to the beginning, and that creates more of the chart that we understand today. Again, Mendeleev really was big on patterning. So what he actually did is he wouldn't fill in an element that didn't fit. So what I meant by that, even if the next element with the next biggest atomic mass should go into a slot, if it didn't match the properties, he wouldn't put it there. He would actually leave a blank space. So he would still arrange by mass, but he actually left a bunch of blank spaces along the way, and he proposed that these are all elements that hadn't been discovered yet. He was so sure that these elements must be able to be arranged by similar properties that there must be missing elements, and he was right. There was a lot of missing elements. So Mendeleev was actually so sure on his predictions that he was actually able to predict not only what elements were missing, but what the element looked like, and in some cases, how much the element weighed. So he was pretty correct in understanding the patterns of the periodic table. This brings us to the idea of periodic law, and this is actually how our periodic table is arranged, is by periodic law. This is when elements are arranged. When elements are arranged by atomic number, their chemical and physical properties recur periodically. So I've already mentioned this. Elements that are in the same column have similar properties. The fact that that pattern is recurring every about eighth element, that's what we call periodic law or periodicity. Fun word to say. Periods in the periodic table are the horizontal rows. So periods go from left to right. I'll show you left to right. So anything that's a period is left to right. If you count from top to bottom, you actually have 7 periods in the periodic table. That bottom column at the bottom, the lanthanides and actinides, I'll show those to you in a second. They actually don't count as a period. They are included in the periodic table. So you actually have 7 periods, 7 rows going down the periodic table. Groups or families are those vertical columns. So if you go through and you count your groups or families, you actually have 18 vertical columns. And within the vertical columns, you're going to notice similar properties in the periodic table. This is just a little bit fun fact about Mendeleev's predictions and how correct Mendeleev is. So Mendeleev actually was able to predict the element germanium. So germanium was discovered in 1886, but in 1869, Mendeleev actually discovered it. He left it blank. He called it Eka silicon. That's a really fun name. And this is the predictions that he made about germanium. He said that it has a mass of about 72. Its mass is actually 72.39. He said it should be dark gray, and it's actually a grayish white. He said its density should be about 5.5. Its real density is 5.47. He said it should have a high melting point, and the real melting point of germanium is 947 degrees Celsius. That's pretty high. The formula should be so that it combines with oxygen. It combines with two oxygens, so ESO2, and germanium does indeed combine with two oxygens, GeO2, and when it combines with chlorine, it'll combine with four chlorines, and he was right about that. So Mendeleev actually really understood those properties and could pretty much predict exactly what elements were left to be discovered. Kind of cool elements that have been discovered in your lifetime. So we're up to about 118 right now. Many of these in the bottom, if you take a look at the big periodic table on the wall of our classroom, or if I gave you a paper copy, a lot of these in the bottom row here are classified as white. That means that they're man-made. So remember, solids are black, liquids are blue, forgot the word for blue for a second. Gases are red, and anything that's man-made at the bottom is white. This is going to give me a chance to talk about the lanthanides and actinides as well too. So we can see this is our modern periodic table. Our modern periodic table has these random 2 rows at the bottom. These random 2 rows actually should get inserted here and here. So really, this periodic table should be much longer than it actually is. These rows here should actually be inserted here, and our periodic table is actually going to be really long. Why is it not really long? For the simple answer that that won't fit on a piece of paper. So in order to fit it on a piece of paper, we take the lanthanides and actinides. We actually don't use them very often in grade 11 or grade 12 chemistry. We just place them at the bottom, and that actually leaves room to fit all 18 columns across this middle part here. So your periodic table of elements, I shared a digital copy with you that looks very similar to this, so you can actually see how it's organized. We've got it organized by family here as well too. So we're going to go ahead and talk about families, and families are elements that have similarities. So you've learned some families already. You've learned the alkali metals, alkaline earth metals, you've learned the noble gases, the halogens. We're going to take a look at some other families as well too, and what they may have in common in terms of properties. So this here is actually just a nice labeled periodic table that shows you all the families. Before I look at families, I do want to mention that there are alternate periodic tables. So this isn't necessarily the best representation for shared properties. It's really just the most convenient table that we can fit onto a piece of paper. So in all reality, when you think about it, helium and lithium are very similar. Helium and lithium only differ by one proton, yet they're on different sides of the table. So really, a good periodic table would actually be circular, right? That way you can actually see the increasing number of protons, yet the columns would still remain the same. So it's pretty hard to carry a circle around. So these alternate periodic tables, while they're very, very accurate, just aren't as convenient to use. So an alternate periodic table here is kind of a way for us to see the increasing atomic number. So we can see the increasing atomic number, yet you can see it's still organized by traits, and you can see it's still organized by properties. This is incredibly hard to read, so this is why we don't use this in chemistry class. Another alternate periodic table is here. It's more organized by levels. So again, you can actually see the different energy levels as we go through. This helps a little bit with electron configuration, which we study in grade 12, but again, not incredibly easy to read. So our periodic table, it's arranged by first of all, it's arranged into vertical columns called groups, and that group number is going to tell you the number of electrons in the outermost shell. There are 18 groups. So just a reminder, in order to tell the number of electrons in the outermost shell, you're going to start counting from here. Anything in group 1 has 1 valence electron. Anything in group 2 has 2 valence electrons. Anything in group 13 over here has 3, 4, 5, 6, 7, 8. So you did start learning that in grade 9. However, I appreciate grade 9 was a long time ago. So if you want, I would actually maybe pause the video right now. And if you've got a paper copy of your periodic table, it's your baby. You can do whatever you want with it. I would maybe write the number of valence electrons at the top here. Because as we move into Lewis diagrams, you're going to be expected to know off the top of your head how many valence electrons something has. So 1, 2, 3, 4, 5, 6, 7, 8. Notice that I skipped over this big column here. We're going to talk about this big column in a second. The reason that we don't label the number of valence electrons here is because it actually can vary. So we'll talk about that a little bit more in a second. All right, elements in the periodic table are grouped into families. Anything in a family has similar properties. So anything in a family has similar properties. So anything in this family is going to have similar properties. Anything in this family has similar properties. Anything in this family has similar properties. And that's actually how the periodic table was originally arranged. We also have those horizontal rows called periods. Again, periods, there's 7 of them in the periodic table, and that's actually telling you the number of shells or the energy level. So again, if we go back to our periodic table up here and I take a look at it, I would call this row here, hydrogen and helium, the first energy level. And when you draw a Bohr-Rutherford diagram, it's going to have 1 ring. Here, lithium, beryllium, boron, carbon, that's going to be your second energy level. And when you draw your Bohr-Rutherford diagram, it's going to have 2 rings. My third period has 3 rings or energy levels, 4, 5, 6, 7. So every time you take a step down the periodic table, you're adding an energy level or a ring to your Bohr-Rutherford diagram. This is actually going to matter for periodic trends, which is what we're going to be talking about next. So again, elements that are in rows actually don't have similar properties at all. The only thing that they really have in common is the number of energy levels or the number of shells in the Bohr-Rutherford diagram. Let's take a closer look at our groups now. Let's take a look at group 1, and that's our alkali metals. So it's kind of tricky because on your periodic table, hydrogen is in group 1. Hydrogen is not an alkali metal though. Hydrogen is not a metal at all. It's a non-metal. So hydrogen is actually kind of an element on its own. It really doesn't have a group. It's placed in that row, in that column though, because it's got similar properties to the alkali metals. So it's very reactive. Alkali metals are very reactive. But when we're defining alkali metals, lithium, sodium, potassium, rubidium, cesium, and francium, those are our alkali metals. They're all said to be very reactive. They're actually so reactive that if you drop them in water, they will catch on fire. I have a video of that later for you too. They're soft solids at room temperature. They're malleable and they're ductile. A little bit more about alkali metals. Why are they so reactive? They are actually so reactive that you can't find them naturally in nature. So you're not going to find a chunk of sodium. You're not going to find a chunk of potassium just kind of floating around on the ground. They're so reactive because they only have 1 valence electron. Remember that we're going to get more into this in Lewis diagrams, but remember Bohr-Rutherford diagram is happy when the outside shell is full. In this case, we're not full, we have 1. It's really, 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 really easy to lose 1. So since it's so easy to lose 1 valence electron, that happens often, it happens easily, it makes the alkali metals very reactive, it makes them very likely to occur in ionic bonding, and it means that their reactions tend to be a little bit more violent. If we move on to group 2, we're going to be talking about the alkaline earth metals. So beryllium, magnesium, calcium, strontium, so on and so forth. These are considered to be reactive. Notice I took the word very out. So they're reactive, they're not very reactive. They're not as reactive as alkali metals. They're also solid at room temperature, and they all have a metallic character. So they don't look the exact same, but if you take a look here, they all look fairly metallic. Um, all alkaline earth metals have a valency of 2. So what this means is they have 2 valence electrons. Now 2 is not as easy to lose as 1, so that's why they're not very reactive. That's why they're just reactive. You are going to lose 2 valence electrons, so the overall charge is going to be 2 plus in an alkaline earth metal. They have 2 electrons in their outer shell, and since they're ready to lose those electrons, they are involved in ionic bonding. Group 3 to 12, so that's that column that we kind of flipped over before. We didn't say the number of valence electrons. Those are the transition metals. So the transition metals actually have what we call variable valency. So the number of valence electrons that they're going to gain or lose is actually going to change. This is going to make a little bit more sense when we look into our electron configuration or a new atomic theory next year. So right now, if you're trying to picture a Bohr-Rutherford diagram and how it might vary, depending on how many electrons are gained or lost, it's going to be really hard for you to do. This is one of the limitations of Bohr-Rutherford diagrams. So Bohr-Rutherford diagrams makes it really hard for us to understand how valency can vary, how you might be just as happy giving up 2 electrons as you are giving up 4 electrons. But once we actually get to electron configuration next year in grade 12, that may make a little bit more sense. For now, I'm asking you to trust me, and I'm going to show you when we get to naming how to actually tell how many electrons a transition metal is going to give up. So our transition metals are again in this area here, and they're actually going to have those variable charges. So do I have it up here? I don't think I do. On some, oh, I do. Can I zoom in? Can you see it? Now you can't see it on here. So on some periodic tables, if you've got your paper copy in front of you right now, you're going to see on the periodic table for these transition metals, right underneath the name, you're going to see multiple charges listed. So if you look under, for example, iron, you're going to see multiple numbers listed. That means that it's a transition metal. That means it has variable valency. However, if you look under zinc, you're only going to see 1 number listed. You're going to see the number 2 plus listed. So that tells you that it's actually not necessarily a transition metal. It's actually straight up telling you the charge. Take a look at copper. It's got variable valencies. It's got more than 1 number listed. And then if you take a look at silver, it's actually only got 1 number listed, 1 plus. So that's how you can tell if something is a transition metal. If you actually take a look at your periodic table, and it'll actually tell you the charges. Take a look at your legend. It'll show you where your charges are. If it's got more than 1 charge, it's a transition metal. If it only has 1 charge, even though it's grouped with the transition metals, it has a fixed charge. All right, let's take a look at what we call the inner transition elements, and these are our lanthanides and our actinides. So our lanthanides are considered to be soft metals. They can be cut with a knife. These elements are actually so similar that they're very hard to separate out when they occur, which they often do. So lanthanides and actinides were actually discovered much later, and that's because they all look very similar in terms of metal. They all look like soft metals. Actinides, on the other hand, they're all radioactive. The nuclei of atoms of radioactive elements are unstable and decay to form other elements. So actinides, even though they do exist, often decay into other elements. Where you can find the lanthanides and the actinides on the periodic table, you can see them in this picture here. We've got the lanthanides are on the bottom, very similar to each other. The actinides, all radioactive, are all down here. Remember, the lanthanides actually fit in here on the periodic table, and the actinides actually fit in here on the periodic table. We don't really look at them very much this year, just based off of the compounds that they form. Now we're going to go back to a more familiar group for you. The more familiar group is the halogens. So group 17 is your halogens, fluorine, chlorine, bromine. They are all very different. So for example, iodine is a halogen. It is a solid. Bromine is a halogen, it is a liquid. Chlorine is a halogen, it is a clear gas. So they actually don't have a lot in common in terms of physical properties. They could be a gas, they could be a liquid, it could be a solid, it could be, but they are all indeed non-metallic. What halogens do have in common is they are considered to be very reactive. They're considered to be just as reactive as alkali metals. Why? Because they only need to have one more valence electron to be full. They're considered to have 7 valence electrons. 8 is full for valency. So since they only need to gain 1, that's really easy to do. They are very, very, very reactive. And they tend to form bonds with metals, but they can also form bonds with nonmetals, sharing 1 electron. And our last are noble gases, also called inert gases as well too. Inert means non-reactive. So we've got helium, neon, argon, krypton, xenon. What they have in common, they are all gases. Who knew? Noble gases are all gases. And they are all non-metallic. They are very, very, very unreactive, and they're said to be stable. We tell you in grade 11 that noble gases won't form compounds. That's not true. Noble gases will form compounds. I'll show you how in grade 12. So noble gases are considered to be stable. Why? Because of their number of valence electrons. All noble gases have 8 valence electrons, with the exception of helium, which has 2. But the key is they are all considered to be stable. All of them have a full outer shell. Since their outer shell is full, they're not looking on gaining. They're not looking on losing. So we say that they're considered to be full, or they're considered to be inert. That's a little bit about the patterning and periodic table. Now what we are going to look at next is we're going to look at atomic trends. So we're going to look a little bit more at some of the hidden trends that actually exist in the periodic table and how to understand them. So tune in next time when we keep talking about the periodic table.